All right, last two examples. So it says make a table. So what you would do with your calculator, you would set one equation equal to the left side, another equation equal to the right side, and you just look at your table given the x values. And let's see what you would get. I have it on my calculator here. So for the one, oh, let's see, where do we want to start? Let's go -3, -2, -1, 0, 1, 2, 3. All right, y2 is equal to x, so these will just be the exact same values. Now y1 will be determined by the function we have in place. -3 would spit out -3.2 according to my calculator, -2.25, -1.3 repeating, -0.5. Plug in 1, you get 0. Plug in 2, you get an error. Plug in 3, you get 4, and so on and so on. All right, so when you plug in 2, you get an error, which makes sense. That's just when that's not defined right there. So I'm going to base it off of that. So if you look at your table, something happened right here. Y1 was smaller than Y2. Highlight some of that. -3.2 is smaller than -3. -1.3 repeating is smaller than -1. 0 is smaller than 1. So for this entire area, it does not satisfy this inequality where we want it to be greater than. After that error point, and if you plug in more, you see the y1 represented, that represents the left side, is greater than the right side, which is just 3. So this inequality, with this table, we have our error point. Before and after that, we can tell when it's greater than or less than. So for this one, this inequality holds true where the left side is greater than the right side for all x's that are strictly greater than 2. If you were to solve algebraically like we did the previous ones, you will get the same result. If we were to graph it, I don't want to graph that. So there's our answer. Take this back. Move that over there. If we were to graph this, each side, it would look like, so y equal to x would be this line here. That there is y equal to x. For the left side of the function, we have a 2, we have our vertical asymptote at 2. Give me dashes. So if we graph the left side, and we're not at that point yet of graphing this type of rational, you can have an oblique asymptote, which is the y equal to x in this case. The graph would look like this. All right, so graphically, you can also tell when y1, so here's my y1, is greater than y equal to x. That's when it's above it. Everything down here, it's less than, it's below y equal to x. And then once you pass this 2 mark, it's above the y equal to x line. So graphically, that's how you would determine it as well. When x is greater than 2, this graph is finally above the line y equal to x. All right, so table and graphically there is that one. Final solution, x is greater than 2. Solve it algebraically, you get the same result. So you can solve with a table, a graph, and algebraically. All right, and the last one, this word problem here. From 1990 to 2001, the number of doctors in thousands can be modeled by that function. T is the number of years since 1990. When were there fewer than 800,000? So this gives you in thousands, so we're going to let D be just 800. So when were there fewer than 800? All right. So when were there fewer than 800,000 doctors? So our inequality looks like this. 1,300 t squared plus 79.7. And for this one, you would graph both sides. You want to solve it graphically. So y1 will be this side of the inequality. Y2 will be that side of the inequality. And you want to find out for what t values is y1 below, less than, y2. All right. With your calculator, you'll find out that they will cross at t equal to 9.005. So there were fewer than 800,000 doctors 9 years since 1990. So we're looking at the year 1999.005. So before that t value, that the left side was below the right side, the 800. So before the year, to answer the question, before year 1999, there were fewer than 800,000 doctors. Okay, graph them in the calculator, you get a better representation of what I'm talking about. It'll be similar to this one. In any case, they cross at 9.005, so 9 years since 1990 per the question right here. So before that, you had less than 800,000 doctors. So that is the solution to that one. And that is it for these notes.